Okay, in this video, I'm going to give a brief description of the humoral immune system, and that's the B cells or B lymphocytes, how they become educated or mature, and then how they become activated and what their functions are. I'll try to cover all that pretty effectively. So, what we have is we have B cells, okay, that need to be educated, right? So we have to educate these guys on two things. One is to become immunocompetent. Immunocompetent means that you're able to recognize the specific pathogen that you are built for. So for B cells, they have their own receptors. So I'll put this over here. B cells have their own receptors, and so the receptors are built to fit onto one specific foreign antigen, right? So whether it be a virus, bacteria, whatever it is, okay? So it can bind specifically its receptor to the foreign antigen, okay, which is a little glycoprotein. And so we have self-antigens and foreign antigens. Whenever we have foreign antigens, we'll mount an immune response against it. And so with this specific immune system, this is one part of it, the humoral, which is the B lymphocytes, we're going to have to activate it to become, well, we're going to have to educate it to become immunocompetent, which means it's able to bind specifically its receptor to the pathogen it's specific for, if it ever encounters it. And then two, it has to be non-self-reactive or self-tolerant, which means it doesn't bind to a self cell or a self-antigen and then go ahead and make antibodies against a self cell. So that's the goal, is to have those two things. Immunocompetent, you can do your job, and self-tolerant, you don't attack self, right? Those are two really important things. So when we're educating B cells, what happens is, if the receptor is self-reactive, there's a couple different ways we could do this, okay? One is we can destroy the cell through apoptosis, which is programmed cell death, and we just get rid of it, okay? However, if we're able to edit the receptor, where it is non-self-reactive or it is self-tolerant, so it's not binding to self, and then it also can bind to the pathogen it's specific for, then we can edit the receptor, and then that cell will continue to, it will finish maturity, right, or its education, and then we will put it into the lymph system so that it may or may not encounter that pathogen if we ever encounter it, okay? Now, that's the activation of the B cells. If self-reactive B cells escape, we can track them down and inactivate them, and that process is called anergy. All right, now let's move to the actual activation process. That was the education process for the B cell. The activation process is this. In fact, let me get my receptor back over here. And so this is going to play both a receptor and an antibody. And some types of antibodies actually do serve as B cell receptors. So that makes some sense. Okay, so we've got this receptor on the B cell, okay, and it fits specifically to a specific, as I said, a specific conformation of a glycoprotein, which is an antigen, that is on some type of virus, bacteria, whatever it is. And so if it encounters, now it is seeded, we seed these educated cells into the lymphatic system, and if it encounters that pathogen, it's going to bind to the receptor. So it's called an antigen challenge. The antigen challenge is the B cell's receptor binding directly to the foreign antigen. Okay, so this will be the foreign antigen, I bind directly to it, and then that B cell becomes activated. What's going to happen is it's going to replicate into a whole bunch of cells called clone cells. So it's going to make a bunch of replicas of itself. And then those clone cells are then going to change. They're going to differentiate into a different type of cell called a plasma cell. Okay? Now, the plasma cell is the one that has the ability to make the antibodies. So we're going to differentiate into the plasma cell. The plasma cell is then going to make antibodies. Now this process takes about 3 to 6 days to happen. Once it happens, we start cranking out antibodies, or plasma cells start cranking out antibodies at about 2,000 molecules per second, and that lasts about 4 or 5 days in a primary or initial response. And so what's going to happen is also in this process, by the way, from going from clone cell to plasma cell, you are going to need T cells called helper T cells to help modulate that process and that transformation or differentiation process into a plasma cell. So to become active, the B cell is going to need helper T cells to do that, right? And so I mentioned earlier in the semester with my students that helper T cells actually modulate the entire specific adaptive immune system, because they activate cytotoxic T cells, which we'll see in the next video, and they activate B cells, which we're seeing in this video, or they're essential in the process. And so once that B cell is active into a plasma cell, it cranks out antibodies, again, very, very fast. And those antibodies are going to do the attacking. Now, antibodies do not destroy the pathogens. Understand that we have 4 processes I'm going to super briefly cover. The first process is called neutralization. It's going to bind, these antibodies are going to bind to specific sites on the pathogen. So we'll make this blue guy the pathogen, and the antibody is going to bind to specific sites so that that pathogen, virus or bacterial exotoxin, cannot bind to our cells. Okay, so it neutralizes it. At the same time, by tagging it with all these antibodies, we have done something called opsonization, which means we've marked it for deletion. So phagocytic cells like macrophages will see it and then come engulf and eat this thing up, because again, the antibody is not destroying the pathogen, it's neutralizing it in this case, and then also opsonizing it, marking it for deletion. Now, a second thing is precipitation. You have some pathogens that are really small or soluble, we're going to say, and they can move right through the cell membrane. And so antibodies are going to bind to those and create this larger antigen antibody complex that's going to precipitate it out and keep it from being able to pass into the cell and infect the cell. That's another thing that happens called precipitation. And that actually also opsonizes as well, right? It marks it for deletion. So macrophages will come over and eat that complex of antibody antigen, okay? And so another process is called agglutination. Agglutination is if you have a mismatched, let's say, blood type. What's going to happen is the antibodies are going to bind to the mismatched cells. So if I'm type A and I receive type B blood, the recipient always attacks, and so I'm going to create antibodies that are going to bind to multiple cells, the red blood cells, okay, of the foreign blood type. And so that's going to clump or agglutinate the blood. And then that's also opsonizing it. Of course, this is very dangerous because then we can block small arteries with that clump of blood cells, and we can also, the blood cells can break and leak hemoglobin into the blood. All stuff I talked about in the blood chapter. Okay. The last process is called complement activation and fixation. And so, by the way, all of these are opsonizing. All 4 processes of antibodies are opsonizing. So complement is a different type of antimicrobial protein. We have approximately 20 of them in the blood, and they have to be activated. And so what happens is when pathogens go to attack a cell, certain pathogens we will have antibodies that will bind closely together on the cell membrane. And when they do that, it activates these proteins, these blood proteins that we have called complement proteins. And what they're going to do is they're going to enhance inflammation, which is a necessary innate process that helps the immune system. It's going to enhance phagocytosis, which is the opsonization that I talked about, increasing that macrophage activity, eating up, this stuff. And the third thing it's going to do is something called complement fixation, where a portion of the complement protein is going to attach to the cell membrane. And so what's going to happen is it's going to cause the cell membrane to rupture or lyse. And so it's going to cause cell lysis of the infected cell. And then, of course, macrophages will come and eat the debris. One thing I wanted to add before I close this out is when we have this primary response, we're going to create memory cells. These are called memory B cells, and they contain all the information that it took us 3 to 6 days to process and start making antibodies for that pathogen. What are they for? Well, this is what gives you your immunity, which is called immunological memory. And so your immunity is based on these memory cells, and if you encounter that exact same pathogen again, that memory cell will immediately divide into many, many plasma cells and produce lots of antibodies. A secondary response is much more powerful. It happens within hours instead of 3 to 6 days. The peak, instead of taking 10 days to peak in antibodies, it peaks in 2 to 3 days, and the peak is way higher, so we're making way more antibodies. They stick around way longer, and they have a greater affinity, which means they can bind better, which means they do their job better. So in a secondary response, you should not get the infection or whatever it is that that pathogen gave you in a primary response. You should be able to fight it off before it gets to that point. And so that's a secondary response. If you have any questions, let me know. Stay strong. I'll see you next time.